My name is Dan Olteanu. I'm professor in the computer science department at Oxford, and I'm working on databases mostly, database systems and theory. And this is a very short introduction to one of my projects called Factorized Databases that took off a couple of years ago. This picture here you see on Factorized Databases showing a table highlighting repetitions in the table. The idea is that a factorized database is a database where these repetitions are avoided, right? So we do not need to store them, we do not need to compute these repetitions. So we can just compress them, and by this I mean factoring out common terms and representing them once. But let me first give you a context. Being a database guy, I look at problems in the world through data management lenses. And what I see there is that data management is a defining challenge of our time. In what sense? Well, first of all, we generate much more data because it's much cheaper to generate this data. And at the same time, thanks to hardware advancements, we can also process this data more efficiently. So this led to a flurry of data sets that are generated by humans, by websites, by sensors, and so on and so forth. And they all require more advanced scalable techniques to process. At the same time, our society is becoming increasingly more computational. We see across sciences, for instance, that now these days people deal with data, experimental data, they fit a model and they try to make predictions. We see, Twitter data being very relevant and people do analysis, sentiment analysis, and so on and so forth. So overall, data is at the center of our society, we could say. Now, over the past decades, we have had the database technology seen as a very robust technology, right? It's ubiquitously, is effectively everywhere, right? A database technology. In fact, one of the most used software tools in the world is SQLite, which is an open source, very small piece of software which is everywhere. Essentially, is used by very many applications on my laptop. It is used on every iPad, on every Android, and so on and so forth. I guess the most popular one would be the zip compression library. But after that is SQLite. But nevertheless, these database systems are not scalable enough. They cannot really cope with these large amounts of data for several reasons. But one reason I'm going to mention to you today is the following. At the very core of the database technology, we have the relational representation of the data, which is a listing representation of records. And this is inherently redundant, has a lot of redundancy by means of how we produce this data in the first place, by means, for instance, of joints, of queries in general, right? But also general programs, triggers, and so on and so forth. And at the same time, although it sounds a bit, I would say, surprising that to this day, I could say this, right? It is only a few years ago that in our research community, people understood finally what means for a query processor to be worst case optimal. What means for a join algorithm to do essentially the work needed in worst case, but not more, right? And that is with respect to this highly redundant representation of the data. Okay? Now, if you would go for a much more compact, succinct representation, yet lossless at the same time, right? You may actually have to redefine the meaning of worst case optimal. Yeah? So, in this sense, the tractability map for queries and also analytics, and by analytics I mean here, for instance, learning regression models, remain mostly uncharted. And this is our goal, basically. In our call to arms, we would like to investigate this. So the current focus is this factorized database project. And as part of this project, the idea is, or our aim is to investigate foundational and systems aspects of scalable data management that comes at the confluence of three different paradigms. One is to compress, and this is akin to the factorization I just mentioned before. One is to distribute, and one is to approximate. And you would like to do this for a mixed workload of database queries, so processing that usually happens inside the database, but also optimization problems, which are usually confined outside the database. But we like to bring them inside the database and see them at the same level as queries. And we like to do this over relational data. Why relational data? Simply because large amounts of data these days is still stored in a relational format, right? And the companies we work with, for instance, in Silicon Valley and elsewhere, they do have data from their clients in the retail sector, for instance, coming in this format. So they will have to learn models over this data. Now, it is true there is also the unstructured data aspect, which should be tackled. But one way to tackle it and to bridge to our work would be, for instance, to use special segmentation techniques, right? Certain techniques that can infer structure from unstructured data and bring it back into the realm of the relational databases. So I will give you now an example of factorized databases in 3 minutes, right? Imagine we have these 3 tables, which is a kind, sort of standard scenario where we store information about houses, where we give the zip, the area, and the price for the house. Then we have shops. Again, within a certain zip code, we have a shop with a name and the hours it is open. And we have also restaurants, also within the zip code and with the name and prices, right? And what people usually do is they merge this information, right? The information is usually is normalized, and after that they want to denormalize it, to bring it back together, right? Okay? How do you bring it back together? For instance, in this particular case, you join on the zip key, right? On this zip column. You join on it and then you build a much larger table. And that would look something like this below. I don't show it completely, but the idea is that if you look at the original tables, I highlighted with different colors the tuples that would match. So the first 2 tuples in house would be paired with the first 3 tuples in shop and with the first 2 tuples in restaurant. That would mean how many possible pairs? Well, combinations, 2 times 3 times 2, this is 12. And then for the lower 2 tuples in each table, if we combine them, we get 8, right? So why is that? Simply because the first tuples in red there, they have the same zip code. So effectively, this merging boils down to doing a Cartesian product of the first part and then a Cartesian product of the second part. And that is the meaning of a join. The join being the most used operation in databases, effectively, right? Has different names in different communities as well, but you can think of it as just being a join. Now, if you look at this join result, you realize immediately that it has a lot of redundancy, right? And this redundancy is necessarily there. Why? Because indeed we have this Cartesian product. The relational databases are materializing explicitly all these combinations. And this is actually the culprit for many systems not being sufficiently scalable. They blow up, the representation and also take time to create that redundant representation. So instead, the factorized representation simply factors out this information. So how would we do this? We know from the query that given a particular zip code, the information we had about houses would be independent of the information we have about shops or about restaurants. So we do not necessarily need to eagerly materialize their combination. We can keep them separately. We can keep them in a more symbolic representation. This is why here, as you can see, we have 2 choices for the zip code. That would be OX1 and OX2. And under a zip code, OX1, we store symbolically the product, the Cartesian product of these combinations from the different tables. That is, we store separately information about the area and the price, then restaurants and opening hours, and then shops and prices. Okay? We do not materialize. It is a lossless representation, but it's a much, much more compact representation. It can be arbitrarily more compact in practice, in fact, right? And we can compute it very, very directly, right? We do not need to go over the big redundant table and then, factorize it. What did we use to do this? First of all, the conditional independence, which is apparent in the query. The query tells us the way we join. That is, you join on zip. That is, if you give me a zip value, then the information I put together would be independent, right? And this is a principle used throughout computer science, in fact, to speed up computation. And the second thing is we really use here the distributivity of Cartesian product over union, similar to the operations product and summation you would use in a semi-ring or in a ring, right? This is exactly what we do here. And questions we ask ourselves and we answer positively would be, which factorized joints have worst case optimal size? That is, if you look at possible structures that would exploit the conditional independence in the data, what would be asymptotically the smallest? Can you characterize, given any join query of your database, what would be the worst case optimal size for a representation of its result, regardless of the database, right? And we can answer this question. So that is the interesting thing. And we can also compute the factorized joints worst case optimally. That is, we know what would be the worst case optimal representation, and we can go from the input database to that representation, essentially using time to write every single bit in the result. Modulo log factor for initial sorting of the tables. But that would be it, right? And that is much, much faster than computing a join materializing as we did on the previous slide. To give you a simple example, imagine that those tables I showed you. Now I constructed 25,000 zip codes in every table, and I take S records per zip code and relation in every table. Now, if you do the usual standard representation, then you will be cubic, because you'll basically join for a given zip S with S with S records from the different tables. So as S increases, you expect a cubic decrease of performance for the standard join. But for our factorized join, we stay linear because we avoid this explosion. So this is why, if you look at the table, the plot here, you see that the two lines below, the solid lines, would represent time and space needed in our case, right? So the time would be in seconds, would be up to 10 seconds to do up to a scale factor of 15. Whereas the other guys will actually take several orders of magnitude more time, but also space. Yeah, space is on the other side. The size is on the y-axis in log scale as well. Okay, so that is actually, at the time we observed this, we said, oh, this is actually very interesting. But can you do anything with this representation? And the beauty of it is that the answer is yes. This is a lossless representation, and we can do lots of things on top of it. We can, for instance, train regression models. And this is what we did next, right? So we said, can we actually learn, let's say, a linear regression model on top of this factorization? We, in collaboration with our industrial partners, for instance, LogicBlox, what we did, we built a tool that would learn various types of regression models, like factorization machines, like ridge linear regression. We could do also logistic regression, SVM, PCA, and now we looked even beyond to decision trees and so on. Right, on top of the database, because that was their setting. It was not a setting we came up and told them, no, you should learn over the database. No, this is what they did, but they used huge amount of Amazon infrastructure, computing power, to just train their models. Now with this approach, they were able to go, sometimes orders of magnitude faster, to train the same model with the same accuracy, just by avoiding the redundancy in the data and in the computation. And how we achieved that? Well, first of all, we had to exploit the relational structure. We are in a confined setting. We know we deal with relations that have certain schemas, that have certain functional dependencies or joint dependencies holding on them. So we can effectively exploit that. We do not learn a model on some generic decision, input matrix, right? We learn it on a particular relation, which is the result of merging together tables from the database. Then a second thing we did is that we pushed the learning task inside the database query engine, so as to avoid the import-export time. And I will show you how this is usually done in settings out there. And then we factorize this computation. So let me actually say a bit about why we do this in database analytics. So data is large. The code is reasonably smaller, right? The kind of standard thing people do these days is that they move the data between the code, because there are several software packages out there, and you say, now I want to do this process in this database system, and then I export the data, I fit it into a new format for statistical package like R, I do something there, and I move the data from there, and so on and so forth. Why should we move the data? We should move the code, right? The data is very expensive to move. Sometimes you cannot even move the data, right? You are not even allowed to move the data. So we avoid this expensive step, and I will show you some numbers, performance numbers, that to basically explain that this takes much more time than just doing the end-to-end solution, right? Then we like to exploit database technologies. They do have effective, technology on joints, indices, and all this stuff, right? So we should exploit that. And then we can then build better models using larger data sets, because by using factorization, we can fit more data, for instance, in memory, or we can process in one go more data than actually we could do with the highly redundant data set. And then the perhaps surprising thing we realize is that if you really look, you stare enough at the code to do, for instance, to learn a linear regression model, you realize that actually the entire code that deals with data can be phrased as join aggregate queries, but very many of them. They are almost the same, but not quite. But we realize that by actually evaluating all of them together, computing all of them together, we can actually share massively the computation across them. So we can solve, for instance, millions of aggregates together within some hundreds or thousands of seconds, right? And then there is indeed a part in every training model, for instance, if you don't want to compute the exact solution, which is the fixed point computation, which is necessary for convergence. But that you can do it after you touch the data. Okay? So this is the depiction of what we actually do. So the out-of-database analytics, which is the kind of standard analytics task, is you go from the feature extraction query on the left, right, which looks over the database and says, this is the information that is relevant for my model. Then you materialize the result of the join that puts together all these features, and then you ship this to the ML tool, and then you compute the model, exemplified here by the theta star, right? Our approach, however, is different. We actually look at the feature extraction query. We start also with the model, and the model, we actually reformulate it into this bunch of queries, which together with the feature extraction query are sent to this engine we have, a factorized query engine, that rewrites them, optimizes them, and knows how to compute them efficiently, right? And they are then evaluated, and the result of them is actually fed into this gradient descent trainer, for instance, which will then do the fixed point computation for convergence. And then we end up with theta. So what we did is specifically here, we avoided materializing the result of the join, which is very large and highly redundant. And also, we somehow derive from the model the actual aggregates, which we would compose together with the feature extraction query and get a more optimized code. So there is actually, we showed that there is a big complexity gap we can achieve by doing this. In fact, I will not go into details, but imagine the following. Imagine that the time it could take to do the red approach, which is the standard approach, would give you a complexity which is size of the database to a number n, where n could be the number of relations in the query. Instead, the green part, which is us, essentially reduces from n to another number, which is called the fractional hypertree width of basically the queries we have to do there, right? And this can be arbitrarily smaller, right? For many queries, for instance, so-called acyclic queries in the database world, right? The fractional hypertree width is 1, whereas n can be as large as the number of tables in the database. So we gain huge speed. And in practice, this translates into performance numbers. I will not insist on the table too much here, only to say the following, that we looked at a retailer data set from our industrial partners. The full one would have 86 million tuples. And if you look at the features, we have about 3,600 features in it, right? So we like to build models with that amount of features. And we transform them into about 145,000 aggregates, which we could evaluate within 380 seconds, right? To get an impression. In contrast, and our approach to just do the aggregate and join, we take these 380 seconds. The other ones do not really cope, right? We stopped Madlib, which was the best solution we compared against, after 24 hours, okay? For a much smaller data set, we realized that, for instance, the time it takes for our approach to just do the end-to-end solution, which is about 25 seconds, is half the time it would take Postgres to just compute the join and materialize it, right? If you want the import, that would be more than an order of magnitude higher, right? If you want to do the export-import. And then let alone learning with R or with others, okay? If you go to higher degree models, then the situation becomes even more dramatic. Here, as you can see, we can actually, even for the smaller data set of 17 million tuples, we can get 132 seconds, 135 in total, or 6, right? Whereas the best competitor would take 24 hours or more. Yeah? So this is what we are talking about. We want to effectively understand what is the best way we can factorize the data in computation and then use this, right, for more sophisticated tasks outside even the database realm. And now let me say a few words about the last topic I want to mention today, which is something we started very recently. This is real time in database analytics. In some cases, data sets change continuously. And you like to have fresh, up-to-date models in response, right? How can we achieve that? The easiest solution is obviously every time something changes, you recompute. But there might be better solutions with even lower complexity. And this is what we want to do here. So the standard setting is this. We start with the data set, then we have the analytics, and we produce the result. Now, the setting I just mentioned to you would go like this. We have then some changes in the data. We refresh the data set, and then we get here at the top right a new database with additions. And then we compute again the analytics and get the new result. But that is extremely expensive because you have to do over and over again the same task. Instead, what we want is to look at the analytics task to derive a special kind of so-called delta program, which is a much smaller program, more efficient program, that together with the changes and the previous result can compute you for you directly the update to the overall result, right? And that can take much less time. We deal with things that may take, for instance, constant time updates, whereas if you evaluate them from scratch, may take thousands of seconds. Okay, and our approach is actually unified. The unified framework to do this to implement this sort of idea for a multitude of tasks. We very recently showed that we can do this obviously for joint aggregate queries. We can do it to, for instance, compute the gradients for least squares regression models, to do matrix chain multiplication, to do inference in probabilistic graphical models, and so on. It turns out that all problems are more or less the same. If you have a unified way to treat them, then you suddenly are in for a unified solution. But the key to unification was that everything that had to do with the data, the in-database computation, was done the same way for all of them. The only difference resided in a special way to model the different applications. And that was modeled using the mathematical tool of a ring, in which we define what means to add two elements from a ring, what means to multiply them, what means when you actually have a negative element added, which is basically a deletion, or you add a positive element, which means you insert. Okay? So this is what we did. Sorry, there is no multiplication. The 0 there, the first 0 should be a multiplication. It was a copy-paste. And the key to performance was triple log factorization. So we did the kind of factorization I mentioned before. For the delta processing, we compiled this to optimize C++ code. Right? We understand how to do this for the triggers we create. Then we also factorize the representation of the result if this is too large, so we can maintain the representation, the factorized representation of a query result. And for bulk updates, we look at them and we can sometimes factorize them akin to the way we would do tensor decomposition, right? And in practice, just to highlight a bit, our approach is FIVM is in blue, and you see it at the very top, the top figure would show you the throughput we can achieve for that 86 million tuple database, where we insert it into all the tuples in a round-robin fashion, right? So as to basically process the whole data. So on the x-axis, you see the fraction of the stream trace processed. So we've gone from nothing in the database up to 100% in the database. Everything is in the database. And we show how we process this, how we can refresh effectively our views, or in other words, our results, right? And we achieve almost 10 to 7 throughput. That's 10 to 7 tuples per second. And this uses a standard Azure machine, which is actually, thankfully, Alan Turing made it possible for us. And the other approaches are below. The one that actually is the standard one is the one, the lowest one over there, which is about 3 orders of magnitude lower and doesn't finish after about 10% of the stream. Below, the figure below here, you can see the actual memory space used, right? And we are in blue, and as you can see, we stay below the others, okay? And this is because we represent data factorized, right? The others have to actually represent much more data, orders of magnitude more. These jumps you see in the pictures there are there because every now and then we have to reallocate more space. So we need every now and then more time, you know, to reallocate, to double the size of our buffers. And that, you can see also the top figure that has these spikes in performance, because then basically we do not have throughput anymore as good, right? We have to, you know, take time to do the reallocation. And if you want to find more, if you are intrigued about that, I'm very much interested in actually talking more about this collaboration. We have positions open even. There is a talk on database learning tomorrow, thanks to Nath being here, right? In the Turing Logic seminar series. Then there is an advanced 3-hour Turing data science class in which I will go in more detail over aspects of this, like joints, what people did to solve joints efficiently. And then, well, if you want to find more, we have a website, FDB Research, GitHub.io, and there you have plenty of resources. Thank you very much for your time.